So we're going to talk about series. Oh, I should type that right. Maybe like the date and stuff. Yeah. See today, May 15th. We're talking about series. Series. I feel like the words for series and sequences are kind of unfortunate because I feel like it's really easy to kind of accidentally interchange them. So we say series. We also often say a sum because a series is just a sum. Typically, we are mostly going to be looking at infinite series, but you could look at a finite series. So for example, a finite series could be something like the sum from n equals 1 to 10 of 2n plus 1 over n squared plus 2. And then you could actually write out all the terms. So all this notation means here, this sigma notation, is that we're starting at n equals 1 and we're substituting that value in, and then we're increasing n to 2, 3, etc., all the way up to 10. So if I wanted to write this out, it would be 2 times 1 plus 1, so 3 over 1 plus 2 is 3, plus, then we plug in 2 and get 5 over 6. We plug in 3, we get 7 over 11, and so on and so on. 9 over 16 plus 2, 11 over 25 plus 2. Probably pick too large a number here. Oh, well, that's fine. 13 over 36 plus 2. 15 over 49 plus 2. 17 over 64 plus 2. 19 over 81 plus 2. And finally, 21 over 100 plus 2. The idea here is that we're just starting at n equals 1, we're ending at n equals 10, we're getting every integer in between, and then we're adding them all up. So the only difference between, well, the main kind of thought difference between a sequence and a series is a sequence is a list of numbers. Typically thought of as like a sub 1, a sub 2, a sub 3, a sub 4, etc. Whereas a series is the sum of that list. A sub 1 plus a sub 2 plus a sub 3 plus a sub 4, etc., etc., etc. Most of the time, we're going to be looking at infinite series. So for example, here is an infinite series. Say the sum from n equals 1 to infinity of 3n divided by n plus 1. A lot of the time, our series will start at n equals 1 or whatever letter we're using for our index. But it doesn't have to. It can start at n equals 0 or n equals 5 or really any integer, actually, although usually we're starting at a non-negative integer, like 0, 1, 2, 3, etc. So if I start writing this out, here are my terms. I'm going to get 3 over 2 plus 6 over 3 plus 9 over 4. The way I'm writing this pattern out is just by increasing the numerator by 3 every time and increasing the denominator by 1 every time. So we need 12 over 5. And I don't really need to write more terms. It's not super helpful. That's what's going on here. Now the question is, does this series converge or diverge? To be more specific, right? Converge meaning, does it, in this case, add up to a finite value? Or does it not? And then again, the not here can be a couple different things. It can either not converge, it can diverge by either blowing up to infinity, or getting negatively infinitely large, or oscillating back and forth between a couple different things. Those are typically the way we think about something diverging. So in this case, well, it seems like the terms are getting bigger. Well, maybe not actually. It might not actually be getting bigger. Well, here's what they're actually doing. So we look at the sequence, and this is a common tactic. So we look at the sequence. A sub n equal to 3n over n plus 1. And I would say, you know how like in 16b, when we did integration, a lot of the time, the first thing we would always try is to see if you can do a U sub. That was a pretty common tactic for anti-differentiation because it often worked. It was always worth looking at. Well, in the same sort of way, what we're about to do is always worth looking at when you're trying to see if a series converges or diverges. Let me change this real quick here. So hey there, Manuel. Let me fix this here. Let me pin myself. So if we look at the limit as n goes to infinity of our sequence, I'm going to get the limit as n goes to infinity of 3n over n plus 1. Again, noting that both the numerator and the denominator have the same degree, that limit's just going to be the quotient of those leading coefficients, which is going to be 3 over 1, which is 3. So the sequence converges to 3. The series is going to diverge. And here's why. What's essentially happening here is if we look at our series, the sum from n equals 1 to infinity of 3n over n plus 1, what's happening is, right, we've got these first terms here, 3/2, 6/3, 9/4. But then when we go way, way out to like the 100th term, the 100th term is going to be 300 over 101, which is pretty close to 3. And if we go even further, like to the 1000th term, we're going to get 3000 over 1001, even closer to 3. And we're going to do this forever. So what's in essence happening is that we're adding up an infinite number of numbers that are all really, really close to 3. And if we add up 3 plus 3 plus 3 plus 3 plus 3 plus 3 an infinite number of times, we're going to get infinity. So this series, the sum, or the series, I say sum and series interchangeably. I accidentally say sequence interchangeably too, but I'll try not to because it's not interchangeable. We say the sum from n equals 1 to infinity of 3n over n plus 1 diverges. If you wanted to be more explicit, you could say diverges to infinity. Although we often don't really care how a series diverges, we just care that it diverges.
It's never incorrect to specify, right?
Yes, it's just sometimes you can't specify. In fact, so that brings us to the next example, which I think is a classic. The infinite series. So let's call this number 2. Number 1. The infinite series, the sum from n equals 0 to infinity of -1 to the mth power. So I start writing out terms. I get 1 plus -1 plus 1 plus -1 plus 1 plus -1. And it just keeps going this way. And so this is where you might be able to convince yourself of the wrong answer. You might say, well, James, it's always going to be 0. Because 1 plus -1 is 0 and do that forever. But here's what we really have to do to correctly observe what's happening. We're going to look at what's called the partial sums. So S1 is the sum from n. I don't love the way I've done this, but fine. I really don't love the way I've done this. So I should be more specific here. When we talk about partial sums, we usually talk about writing just the first term. So S1 is the first partial sum, meaning you're adding up the first thing, which unfortunately with this notation is going to start at n equals 0 and end at n equals 0, which is kind of funky. I'm just getting -1 to the 0, which is 1. So the first partial sum is just 1. The second partial sum, I'm not going to write it this way. Yes, I am. Now I'm adding up the first 2 terms. I'm getting -1 to the 0 plus -1 to the 1, which is 1 plus -1 which is 0. The third partial sum, I'm not going to write it all out. So I could do from n equals 0 to 2, but I'm really just going to write 1 minus 1 plus 1, which is 1. And so we can kind of start to see a pattern emerge. Every odd partial sum is going to add up to 1. Every even partial sum is going to add up to 0. So what we could say is the nth partial sum is equal to 1 if n is odd, 0 if n is even. But the problem here is that, well, if we try to take, so the way we typically try to see if a series converges or diverges is we take the limit as n goes to infinity of its nth partial sum. And the problem here is that if we take the limit as n goes to infinity of the nth partial sum, well, it doesn't exist. It's going to keep bouncing back and forth between 1, 0, 1, 0, 1, 0, and that process is never going to end. So this limit does not exist. We don't get close to one and only one particular finite value. So in this case, we would say that this series from n equals 0 to infinity of -1 to the n diverges, and that's really all we can say. We can't say diverges to something because it doesn't. Yeah. So that actually brings up kind of an interesting idea about, I don't want to get, sorry, I'm getting a little ahead of myself with that example, but that's all right. So the previous example we did is an example of what we typically refer to as the nth term test. So the nth term test, often also referred to as the test for divergence, says that basically in a series that's the sum from n equals, doesn't really matter where you start, but let's say n equals 1 to infinity of some a sub n, if the sequence a sub n converges to anything other than 0, or actually I should say, I should back that up. If the limit of the sequence is not 0, meaning it could either be a non-zero finite number, it could be infinity, it could be negative infinity, or the limit itself could not exist. If any of those things happen, then we can say the series must diverge. So as I was kind of saying before, just like how with integration, U substitution is like prolific. We try it all the time. We think about like, can I do a U sub? Can I do a U sub? I should check a U sub. This is the thing you should check when you're talking about seeing if a series is convergent or divergent. You should always be asking yourself in the back of your mind, does the sequence converge to 0 or not? If the sequence, and I'm specifically, if the sequence converges to 0, great, move on. But if the sequence does not converge to 0, we're done. The series diverges. So a couple other examples of this, something like, say, the sum from n equals 0 to infinity of 6e to the n over 2e to the n plus e to the negative n. If I take the limit as n goes to infinity of the sequence 6e to the n over 2e to the n plus e to the negative n, well, I'm going to rewrite that e to the negative n as 1 over e to the n. Sure, I can do that. This 1 over e to the n is going to go to 0, and we're essentially left with a 6 e to the n over 2 e to the n, which is just going to converge to 6 over 2. We could have done more work and divided everything by e to the n like you would, but we don't have to. Notably, 3 is not 0, which means just like in the previous example, we're adding up, or sorry, the previous example, we're adding up essentially things that are really close to 3 an infinite number of times. And if you add up a non-zero finite number an infinite number of times, you're going to get infinity. On the other hand, if the limit of the sequence is 0, we know nothing. Could converge, could diverge. And I want to stress that because that's why this is called the test for divergence. If you're using this test, you can only end up concluding that the series diverges or that we don't know anything. But we never, ever, 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 ever get to say that the series converges by the nth term test. It's not a thing. Actually, it is a thing. Students say it all the time. It's a wrong thing. So don't be a wrong. Don't say the wrong thing. Yeah, let's look at this. So let's look at kind of this classic example. This is probably the most famous series ever, I think. The sum from n equals 1 to infinity of 1, which is known as the harmonic series. And if we write out some terms, we get 1 plus 1/2 plus 1/3 plus 1/4, and it just goes on and on and on and on. Notably, the nth term test is not helpful here. Right, the limit as n goes to infinity of the sequence 1 over n is 0. So that doesn't help. That tells us nothing. Really, the words I say in my head is that if the limit of the sequence is 0, we have to do more. So then, well, yeah, I kind of like doing this now. So yeah, I think you should see how this diverges. So this series is divergent. There's a couple ways of proving it diverges. Here's one way to show it diverges. And I think this is nice to see. I don't think you need to be able to reproduce this, but here's how we can show divergence. I'm going to look at some very specific partial sums. So the first partial sum is just 1. I'm not going to, okay, the second partial sum, yeah, is 1 plus 1/2, which is equal to 3 over 2. And I'm going to point out that 1 is equal to 2 over 2. I'm going to skip the third partial sum. I'm going to go straight to the fourth partial sum. The fourth partial sum is 1 plus 1/2 plus 1/3 plus 1/4. And what I want to point out is that 1/3 plus 1/4 is greater than 1/4 plus 1/4. So that means that this is equal, or this is bigger than 1 plus 1/2 plus another 1/2, which is equal to 4/2. So we'll do 2 more. Sorry, not the fifth partial sum. The eighth partial sum is the next one I'll look at. This to me 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, 7th plus 8. And I'm going to make the same sort of observation here. The 1/3 plus 1/4 is bigger than 1/4 plus 1/4, which is equal to 1/2. And the 1/5 plus 1/6 plus 1/7 plus 1/8 is bigger than an 1/8 plus an 1/8 plus an 1/8 plus an 1/8, which is 4/8. So now this sum is bigger than 2/2 plus 1/2 plus 1/2 plus 1/2, which is 5/2. And you can probably see where I'm going with this. The next partial sum of 16 things is going to be bigger than 6/2. And I can always find the next, right? I'm never going to run out of terms, right? It's an infinite sum. So I can always find the next power of 2's worth of terms. So my next one, so this is, by the way, that's 2 to the 4th. So my partial sum of 2 to the 5th is going to be bigger than 7/2. My partial sum using the first 2 to the 6th term is going to be bigger than 8/2. And the process never ends. So check this out. We can then, we can then say that, and I feel like this is where it's really nice to make this connection here. If we think of this 4 as being 2 squared, this 8 as being 2 cubed, this is 2 to the 4th. This number here is always 2 bigger than that number here. So what we can say is that our partial sum of the first 2 to the n terms is going to be bigger than n plus 2 divided by 2. And then if we take the limit as n goes to infinity of this sequence of partial sums, well, the limit as that goes to infinity, sorry, limit as n goes to infinity is going to be large. So the limit as n goes to infinity of this sum of the first two to the n terms is going to be bigger than the limit as n goes to infinity of n plus 2 over 2, but that is itself infinity. So the thing that I want to point out here that's really important is that this series, whose sequence converged to 0, is still divergent. So this harmonic series is divergent to infinity. All these terms added up together. I'm sorry, you can't see what I'm writing there. Apologies. All those terms added up together add up to, add up to infinity is kind of the wrong way to say that, but the thing they add up to has no limit. It gets bigger and bigger and bigger as you keep adding on more terms, which is not always true. Right? There are other infinite series we'll talk about right now where all the terms add up to a finite number. So let's look at kind of another popular example here. So yeah, I like this one. So let's say we want to find or explore the sum from n equals 1 to infinity of 1/3 the nth power. This is an example of a geometric series because if we write out the terms, the first term is 1/3, the next term is 1/9, the next term is 1/27, the next term is 1/3⁴, etc. The hallmark of a geometric series is that each term is some multiple of the previous term. I should say the same multiple of the previous term. So 1/3 times 1/3 is 1/9, 1/9 times 1/3 is 1/27, and so on. 1/27 times 1/3 is 1/3⁴, and it just keeps going on. So in this example, our ratio is r equal to 1/3. So when we have a geometric series, it is good to identify what that ratio is. So now the question becomes, does this thing converge or diverge? Well, it really, and I kind of do maybe more than I would usually, but typically if we want to see something converges or diverges, we often at least start off by looking at the partial sums to see what they're doing. So we try to find a pattern or a formula for the partial sums. So my first partial sum is 1/3. My second partial sum is 1/3 plus 1/9, which is 3/9 plus 1. I think she did this example in class, didn't she? I mean, that's fine. It's fine to do the same example, but I feel like I could have picked a different ratio. Oh well. My third partial sum is 1/3 plus 1/9 plus 1/27, which is going to be 9/27 plus 3/27 plus 1/27, which is going to be 13/27. Sometimes you can just write out the first two terms and start to see the pattern. I'm noticing here that if the denominator is essentially twice the numerator plus 1. So I can kind of see that, oh, look, this is really equal to, sorry, brain, 3⁵ on the bottom and 3⁵ minus 1 divided by 2 on top. That's how I'm observing that or seeing that. Same deal here. This is 3² on the bottom, and then we have a 3² minus 1 divided by 2 on the top. We could do it that way, and that's probably fine. So what we can kind of say more generally is that the nth partial sum is going to be 3 to the nth power minus 1 divided by 2 over 3 to the nth power, which I would probably simplify as 1/2 times 3 to the n minus 1 over 3 to the n, which I would really then simplify as 1/2 times 1 minus 1 over 3 to the n. And then if we want to see if this series converges, oh, you know what I forgot to do? The thing I said I should do every time is check to see if the nth term test is applicable here. So I should have, before I did all of this, asked myself the nth term test. But this pen is not what I'm loving here. I should have asked, what's the limit as n goes to infinity of 1/3 to the nth power? But then 1/3 times 1/3 times 1/3 times 1/3 over and over and over again just gets smaller and smaller and smaller. So that limit is going to be 0. So no help. But good to at least have thought of, because sometimes it really does help. So then here, if I take the limit as n goes to infinity of my nth partial sum, that's going to be the limit as n goes to infinity of 1/2 times 1 minus 1 over 3 to the n. And kind of just like here, 1 over 3 to the n, as n gets infinitely large, is going to get smaller and smaller and smaller. So this limit is going to be 1/2 times 1 minus 0, which is 1/2. But we'd really prefer not to do this every time we have a geometric series. We don't have to. So there's a very, very kind of more general way to see when a geometric series is convergent or divergent. So let's take a look at that. So let's say we have the sum from n equals, I'm always debating if I want to start at 0 or 1. You can really start anywhere. Let's start at 0. And we're going to do a very generic geometric series. So this is a generic, I can spell generic, geometric series. Specifically here, the ratio is R. And I could write out terms if I wanted to, and actually I'm going to because it's good to see. If I write this out, the sum from n equals 0 of a times r to the n is a times r to the 0 plus a times r to the 1 plus a times r squared, and it just keeps going and going and going. And not surprisingly, each term is the previous term multiplied by r. So a times r is ar, a times r is a times r squared, that times r is a times r cubed, and so on and so on and so on. So that is the defining feature of a geometric series, which you can always multiply by the same thing to the next term. So let's talk about what r could be that would make this converge or diverge. If r is bigger than or equal to 1, then these terms are actually going to get larger and larger and larger, or at least not get smaller, right? You'll have a plus a times the number bigger than or equal to 1 plus a times another number bigger than or equal to 1. So if r is bigger than or equal to 1, in fact, we could use the nth term test and say that the limit as n goes to infinity of a times r to the n is certainly going to not be 0. Because it's going to be a times, well, 1 at the very least. But it could be much, much larger. It could go to infinity. So if r is bigger than or equal to 1, this whole thing diverges. And similarly, if r is less than -1, we're also going to get divergence. Because the limit as n goes to infinity of a times r to the n. If you have a number that's more negative than -1, then you're going to get something that's, right, when you raise it to a larger power, it's going to maybe become positive or negative depending on the, gosh, there's a word that I'm looking for that I can't find, depending on the even or oddness of the power, it's going to get larger and it might be positive or negative. Parity, that's the word I was looking for, the parity of the power. But certainly this limit is not going to be 0. And also, if r is equal to -1, then we have kind of a very special case. We have the sum from n equals 0 to infinity of a times -1 to the n. But this is actually an example we've almost already covered. This is just going to be a minus a plus a minus a forever and ever and ever. And just like 1 minus 1 plus 1 minus 1 plus 1 minus 1 diverges, this also diverges. So these are the values of R that make a geometric series diverge. So a couple examples of this. The sum from n equals 1 to infinity of 3 times 2 to the n is certainly divergent. Look at the terms. The terms would be 3 times 2 plus 3 times 2 squared plus 3 times 2 to the third. Right, the terms are getting bigger themselves. So certainly if we add them all up, that's going to get very, very large. In a similar way, the sum from n equals 0 to infinity of 1/2 times -3 to the n is also going to be divergent. The terms would be something like positive 1/2 plus -3/2 plus positive 9/2 plus -27/2, and so on and so on and so on. And even though each partial sum is going to kind of bounce back and forth between being positive and negative, like the first partial sum is 1/2, the next partial sum is 1/2 minus 3/2, which is -1. The third partial sum we would add back on the 9/2 to be positive, but we're going further and further away from the middle, right? We're going to be larger and then more negative and then more positive and then more negative. And so we're not getting close to any one value. On the other hand, if your ratio is between -1 and 1, then the geometric series is going to be convergent. So if the ratio R is between -1 and 1, which people often write as the absolute value of R being less than 1, then the geometric series from n equals 0 to infinity of a times r to the n converges. We'll find the value in a second here. Something I wanted to point out, but my brain doesn't want to go there apparently. Oh, I know what it was. We often write these as starting n equals 0, but really you can start it anywhere. So you can start like n equals 17 and still figure out what it converges to. And again, Heather, as always, if you have to go, you're always welcome to go. So to figure out what this converges to, we're going to look at the partial sum. So I'm going to look at this is why I don't like using n here, because then when I write the nth partial sum, so I use a capital N usually for my nth partial sum. So my nth partial sum is the sum from, I do not love this terminology, from n equals 0 to, I guess, n minus 1. So I only get the first n terms. That's going to be a plus a times r plus a times r squared, all the way to a times r to the capital N minus 1. We always have to do this weird kind of adjusting, because when we say s sub n, we really do try to mean the first n terms. If we're starting at n equals 0, it means we're ending at capital N minus 1. Okay, so here's some fancy kind of trickery here that we're going to do. So check this out. We're going to take this nth partial sum and we're going to multiply it by r. So r times my nth partial sum. I'm just going to multiply each one of those terms by r. So I'm going to get a times r plus a times r squared plus a times r cubed plus all the way to a times r to the n minus 1 plus a times r to the n. And now we're going to subtract them. So I'm going to take this and I'm going to subtract the nth partial sum I just found, which is a plus a times r plus a times r squared plus all the way to a times r to the n minus 2 plus a times r to the n minus 1. When I subtract these, a lot of things are going to cancel. Let's see here. On the left-hand side, I'm just going to get r times my nth partial sum minus my nth partial sum. On the right-hand side, literally every term cancels except for the very first one and the very last one. So I'm going to get an a times r to the n here, right? That's not going to cancel. And I'm going to need an a being subtracted. But everything else, this cancels with that, this cancels with that, this cancels with that, that with that, that with that. So we end up getting a times r to the capital N minus a. And now just a little bit of algebra allows us to find the nth partial sum. So factor out the Sn here. So Sn times r minus 1 is equal to, whoops, times r minus 1 is equal to, factor out the a times r to the n minus 1. And I think I've written this as kind of a backwards way. We'll fix it. So then we're going to solve for Sn and get that the nth partial sum is equal to a times r to the n minus 1 over r minus 1. And yeah, that is kind of written in a backwards way. The more standard way of writing this is to multiply top and bottom by -1 and to write it as a times 1 minus r to the n over 1 minus r. And now here's the result. If r is between -1 and 1, like 1/2, -1/3, something like that, then r raised to a power that's getting larger and larger and larger means that that value is going to get smaller and smaller and smaller. So what happens here is that this converges to the limit as n goes to infinity of a times 1 minus r to the n over 1 minus r. Oh, sorry. And then that r to the n goes to 0. So that this is equal to just a over 1 minus r, which I think is super. So very specifically, a geometric series written in this format converges to a over 1 minus r. Let me do one example. So for example, the sum from n equals 0 to infinity of 2 times 1/5 to the nth power converges to, really, I wouldn't write this. I would just say equals. Well, let's see. My a is 2, and my r is 1/5. So it converges to 2 over 1 minus 1/5, which is equal to 2 divided by 4/5, which is 2 times 5/4, which is 5 over 2. But the better formula is that the sum from n equals, I don't really care where I start, to infinity of some a times r to the nth power. If I'm starting at, say, k, the best way to write this that I have found in my years of teaching is it's equal to the first term of your series divided by 1 minus your ratio. So in the previous example, the first term of our series would have been 2. So if you plug in n equals 0, you get 2 times 1/5 to the 0, which is just 2 times 1. But more generally, here, this would end up being a times r to the whatever my starting value is divided by 1 minus r. This doesn't always get taught this way, but it is a true formula. It always works that you can do it this way, which I think is nice. So for example, if someone said, what's the sum from n equals 4 to infinity of 3 times -1/2 to the nth power? Well, I would say that's going to be my first term over 1 minus r, which is going to be, well, my first term, if I plug in n equals 4 as my starting place, that's 3 times -1/2 to the 4th power divided by 1 minus -1/2. And then I would probably simplify it. And that's going to be 3 times 1/16. And 1 plus 1/2 is 3/2. So then I would have 3/16 times 2/3, which comes out to 1/8. But that's kind of a nicer version of the usual geometric series formula. It's always just whatever your first term is divided by 1 minus your ratio. Cool. So let's see. I feel like that kind of, oh, we should do, yeah, we got time for one. Yeah. So the other thing that's kind of interesting is you can do the sequence of partial sums thing for a lot of things. So for example, the sum from n equals 1 to infinity of the natural log of n over n plus 1 seems a little tricky. I will point out, if we look at the limit as n goes to infinity of the natural log of n over n plus 1, it's not helpful. Because n over n plus 1, the limit of that's going to be 1, because you have a n to the first over n to the first, and the quotient of the leading coefficients is 1 over 1. And what's the natural log of 1? 0. So the nth term test is not helpful. So then we're going to do something kind of tricky here. And to be perfectly frank, I don't know 100% this is something you actually do in 16C, but I wouldn't be surprised if Piranha did something like this. So I think it's worth the few minutes it'll take. So I'm going to rewrite this natural log of n over n plus 1 as the natural log of n minus the natural log of n plus 1. Because that's a rule I can use with logarithms. And if I start writing out terms, I get the natural log of 1 minus the natural log of 2 plus the natural log of 2 minus the natural log of 3 plus the natural log of 3 minus the natural log of 4. And it seems like if I keep doing this, a lot of things are going to cancel. Right? The natural log of 2's cancel, the natural log of 3's cancel, and so on and so on and so on. But I should be a little bit more particular here. So I do think it's worth looking at the nth partial sum. So let's do this relatively quickly here. The first partial sum is the natural log of 1 minus the natural log of 2. Not very exciting. The second partial sum is the natural log of 1 minus the natural log of 2 plus the natural log of 2 minus the natural log of 3. The natural log of 2's cancel. I should also say here, in this first one, the natural log of 1 is 0. And then the natural log of 1 is also 0 here. So we get the negative natural log of 3. And I think we could probably come up with a formula, but let's do one more. My third partial sum is going to be natural log of 1 minus natural log of 2 plus natural log of 2 minus natural log of 3 plus natural log of 3 minus natural log of 4. And again, we see a lot of things canceling. The negative natural log of 2 and the positive 1, the negative natural log of 3 and the positive natural log of 3. And we're left with a natural log of 1, which is 0, minus a natural log of 4. So I'm pretty sure that I could make the correct guess that the 10th partial sum is going to equal the negative natural log of 11. Because the number that's the natural log of is just one more than the partial sum. So then we can say that, sorry, that's terrible. The nth partial sum is the negative natural log of n plus 1. And then if we take the limit as n goes to infinity of my nth partial sum, the limit as n goes to infinity of the negative natural log of n plus 1 is going to be negative infinity. Because the natural log function gets infinitely large as you keep going to the right. So the negative natural log function is going to be negative infinity, which means this series is definitely divergent. So this idea of finding a formula for the sequence of partial sums, or really I should say finding a formula for the nth partial sum and then taking a limit of that, is something we do a little bit. It's good for the beginning, but then we're going to move on to some other methods of determining if a series is convergent or divergent. Most of the time, if a series converges, we won't actually figure out what it converges to. The geometric series is kind of the special case. For geometric series, we can determine the value that we converge to. For almost any other series, we cannot. All right, that's all I got.